Hi, this is IDL Project Group 9. We're proposing MultiPose fusion, single-view 3D reconstruction using diffusion models with flexible camera pose. The 3D reconstruction methods, they all require the multi-view images to be able to work. From the neural methods to the traditional methods. What if we just only have one input image? Hence, we can use generative AI models such as diffusion models that are already been pre-trained on the billions of image text pairs and really powerful to be able to generate zero-shot novel 2D images. And we cannot train these diffusion models to be able to produce 3D images because we don't have enough 3D object dataset and the computation is massive. So instead we use diffusion models to generate different views from the same object, and then we'll pass it to the 3D reconstruction pipelines. Currently, state-of-art models, they use this pipeline. They input the 2D images to the diffusion models and also the desired output elevation and angle, and diffusion models will output these multi-views scenes from the input image, and we can use these to do the 3D reconstruction such as NEF and etc. Though the challenge that all face is like there's a huge inconsistency between the geometry of these multi-views generated by diffusion models. Hence, researchers put a lot of constraints on the camera pose of the target and input images to be able to make these more consistent. That's what we're trying to improve. The datasets that we use are 3D CAD object datasets from Observerse and Google Scan objects, and we just use a subset of those. For our train dataset, we use 20K rendered objects from Observerse, and for our test dataset to match our baseline, we just use the 30 objects chosen by SyncDreamer, our baseline, to do the evaluation. SyncDreamer, to combat these multi-view inconsistency issues, they use this 3D CNN to be able to get a spatial volume and then like feature map to the fossil volume, and then they use depth-wise attention, this 3D aware depth-wise attention, to be able to condition it on the diffusion model denoiser, and they train on the 800,000 objects of the Optoverse and 800 GPU hours, which is massive. And also, like as I said, they fix the elevation angle of all the target and input images to the 30 degrees, so to have like a more consistent. And this delta V that we see is like a difference angles between the target and input images that they feed to the unit, and unit has been frozen because it's not trainable. The results from the SyncDreamer, as you can see, this is with 30 degrees elevation and it's pretty consistent and good. But as we train this with the 50 degrees and 70 degrees, you can see that the inconsistency is horrible, and this sofa doesn't even look like a sofa anymore. And our approach is using epipolar attention and plucker embedding as an embedding positional embedding. Epipolar attention has been used to mask the attentions for each corresponding feature to the epipolar line pixels. So it just shows attention to pixels throughout that epipolar line between different target views. And plucker embedding has been used to show the attention only to the same ray direction of the other object. So the front face of the doll only shows attention to the front face of the doll in this image. And we fine-tune this new attention networks and along with our 3D CNN attention from the SyncDreamer and then 20,000 object version of the changes we made. The prepared attention plucker embeddings that have been like concatenated to the cross attention here, and then we have like now flexible camera poses with minus 10 to 30 to minus 30 to 60 degrees, and then our dataset also has like a random poses and is not fixed. As for result, as you can see, SyncDreamer, our baseline for elevation of 70 degrees, is very inconsistent in the generative views, but ours is very way better, although we haven't fine-tuned for so many epochs and our data is way smaller. For reconstructed result with the 3D reconstruction methods news. Our evaluation metrics are based on two approaches. One is the metrics for the novel view synthesis. Basically, it's like PSNR and it's similarity metrics and signal to noise ratio between the generated target images and also with the prediction. And we have a matrix for the single view 3D reconstruction, which is a chamfer distance and volume IOU. Basically change the similarity, check the similarity between the 3D reconstructed objects. As I said, since the evaluation takes a lot of time, we just have like 30 objects on the evaluation to match the paper results, and our average currently is very similar, as you can see, to the paper results, although we just fine-tuned on 20,000 subset of the objects. And these are the metrics for the 3D reconstruction. For our challenges and future work, our challenge is like this: the whole pipeline is very computationally expensive. The data collection, the model training, and the 3D reconstruction evaluation. And for the future work, we use like a larger training dataset, larger training epochs, and also adding gradient accumulation because our batch sizes are very small due to the memory constraints. And we're going to fine tune on the objects embedded with the background. Listen, propose.